Good morning, students. Let us start the class. Yesterday, we were discussing the common base configuration. To revise a little bit of the basics once again, in the common emitter configuration, we are feeding input signal to the base and we are taking output signal at the collector. And we had seen three biasing methodologies in the common emitter configuration. Whereas yesterday we had seen the common collector configuration in which input signal is fed at the base and output signal is taken at the emitter. And I had told you that it is not necessary to study the other biasing techniques in common collector configuration because the common emitter configuration is most popularly used because it is going to provide the power gain. It is going to provide the voltage gain as well as the current gain, and it is easy to use. Whereas the other two configurations are not providing power gain, but they have their own advantages. The advantages of the other two configurations we will discuss when we complete the AC analysis. So today, let us go into this common base configuration in little more detail. As I told you yesterday, when compared to the other two configurations, here we require two separate power supplies. The reason is we are taking base as common and we feed input at the emitter and take output at the collector. In fact, this can be in the reverse order as well. We can feed input at the collector and we can take output at the emitter as well because it does not make any difference as far as the AC signal is concerned. As I was telling yesterday, you may think that how can we apply input signal at the emitter where the arrow mark is pointing towards the other side? How can current come into the transistor? Now here we are not going to feed any DC current into the transistor. We are already using DC for keeping the transistor in the active region. Later on we are going to apply small AC signal at the input. Now as per the AC signal, the transistor switching is going to be slightly affected. From the middle of the Q point, it will slightly switch towards the saturation side or towards the cutoff region side, and that is when at the output also we will have a swing in the collector current. That is how this switching configuration is working. When you start working in the labs, you will actually measure the Q point, and when you work with the amplifier circuits, you will understand these concepts more clearly. So in this configuration, we have two power supplies. In the common base configuration, we have two power supplies. One is to the base emitter junction and one is to the base collector junction. We have to give them individually. Now, we have one RE along with VEE so that the base to emitter junction will not get short circuited. And we also have an RC along with VCC so that the base collector junction also does not get short circuited. That is the purpose of RE and RC. There is no need of RB because already there is this RE in series with base to emitter and there is already one RC in series with base to collector. So even though if you think that the base is grounded, again I will repeat, ground does not mean 0 volts. Ground only means our reference point for measuring the voltages and currents. Yesterday I gave you the analogy of the ground level or the sea level. Everywhere on earth, the height is measured of a mountain or a land itself or a country itself uh, with reference to the sea level. So that is also called as the ground level. It does not mean that it is 0 level because below that level also depth can be measured. Okay, same way you need not think that base is at 0 volts in this case. Base will have biasing voltage from this VEE. Now you may again think that this VEE is positive terminal is grounded, VCC negative terminal is grounded, will they not oppose each other? You may think that way, that these two batteries plus and minus terminals are connected to ground, and minus and plus terminals connected to emitter and collector respectively. Will they not cancel each other? No, they will not cancel each other, because the current going through the base emitter junction is different from the current going from the collector to emitter. That is how they will not cancel each other, because there is a beta factor inside the transistor. So I have to clarify all these small things so that you will understand this particular configuration in a better way. Now let me proceed with the DC analysis of this particular configuration. Let us apply KVL at the input side. There is only VBE, IERE and VEE. So it's a straightforward equation. VEE minus VBE minus IERE equals 0. The total supply voltage across this base to emitter junction is VEE. Now this VEE, there will be a drop across base to emitter, there will be a drop across RE. So VEE minus VBE minus IERE equals 0. Or we can find out IE equals VEE minus VBE divided by RE. Now at the output side, VCC minus ICRC minus VCB equals 0. So VCB is VCC minus ICRC. We can straight away find out the voltage between collector and base. Okay. Applying KVL to the entire loop, we can apply KVL completely to the whole loop, including collector and emitter. If we apply KVL to the entire loop, then VCC minus ICRC minus VCE minus IERE plus VEE equals 0. Now, whenever we apply Kirchhoff's voltage law, any drop across the resistor is taken with the negative sign, and when we move in this loop, if we move towards minus to plus in a battery, it is taken with the positive sign. Please remember this. Anyhow, you are going to work with all these analysis even in the course called network analysis. There you are going to use a lot of mesh analysis and node analysis concepts. But as far as the course of analog electronic circuits is concerned, just remember this: any voltage drop across any resistor is basically a loss, and power supply which is applied to the circuit itself is positive, because we conventionally take that current flows from positive to negative. So whenever we apply battery supply to the circuitry, when we move within the loop, if we move from minus to plus, then we put a plus sign there. Now across this RC, it is always a loss. So what we do is, we put a plus symbol here and we put a minus symbol here. Let me put an annotation symbol here. In general, when we move through the loop, generally this is the convention, and here this is the convention. Convention in the sense, when the current flows through a resistor, wherever the current is entering and then wherever the current is leaving, they are respectively given plus symbol and minus symbol, because the current, when it is flowing through the resistance, it is going to induce a voltage drop across the resistance, and the flow of current is in this way, from plus to minus. Again, the flow of current through the RE is also from plus to minus, because it is entering into the RE in this direction, it is leaving from RE in the other direction. Wherever it is entering, we write it as plus, and wherever it is leaving, we write it as minus. Similarly, the current is entering into the collector and it is leaving from the emitter. So we write here again as plus to minus. But in the battery supply you can see when we move in the loop, we are moving from minus to plus here, and here we are moving from minus to plus in VCC. So when we apply the KVL through the whole loop in this manner, imagine we are applying KVL through the whole loop in this manner. We will start with VCC. We are going from minus to plus, that is positive. We are going from plus to minus, that is negative, minus ICRC. Again, we are going from plus to minus, that is minus VCE. We are going from plus to minus, that is minus IERE. And we are going from minus to plus, that is plus VEE. So this is how you will have to understand how to apply Kirchhoff's voltage law into a given circuitry. I did not tell this point till now in any of the classes earlier, because there we used to have a straightforward approach. We simply used to take the power supply which is applied to either the input side or the output side, and there we used to have only a single power supply, and there we used to have only either one resistor at the base or two resistors, one at the collector, one at the emitter. So it was easy to apply the logic itself there. Logically we could arrive at a conclusion that whatever is the voltage applied is distributed among all those components. That was how, without actually thinking about all these plus and minus notations, we could straightforward derive an equation. But in this common base configuration, there are two power supplies and there are two resistors and this transistors collector to emitter region. So remember again, I will repeat this point once again. In any electronic circuitry, when we move from minus to plus, conventionally we write a positive sign to that particular entity or factor. And whenever we move from plus to minus, conventionally we use a negative symbol or minus symbol. And we always consider current moving from plus to minus. So when current is moving from plus to minus, when it is going into the resistor, the entry point is written as plus and the exit point is written as minus. And this is how it is going to induce a voltage drop across the resistance. Whereas always in a power supply, current is again going out of this plus terminal. This is how we apply Kirchhoff's voltage law. There may be different styles in different textbooks sometimes, or in different courses they may use different conventions, but the net result always remains the same. In AEC we follow this particular convention, that when we move from minus to plus we use a plus symbol, when we move from plus to minus we use a minus symbol, and all the minus symbols indicate that it is a voltage drop across the circuitry, and all the plus symbol indicates that it is the power supplies. Now, if at all the direction of this VEE is in the other direction, imagine it will not work in the circuitry. Still, for the sake of example, I am telling you, if the direction of this VEE is in the other direction, then this VEE again becomes minus there. Again, you are going to study all these things in the course called network analysis, where you are going to work out a lot of exercises on node analysis and mesh analysis for arriving at the voltage drop across some passive components. So when there are multiple voltage sources, the convention remains the same. When we apply the direction of the loop, always minus to plus is taken as positive and plus to minus is taken as negative. If you remember that, that is sufficient. Now let me proceed.
Sir, I have a doubt.
Yeah, tell me.
Sir, you told you take the input from the emitter side, but how is it possible, sir?
We are applying AC signal here, right? Just imagine, let me annotate this once again. Imagine here we have VCC. Imagine now there is some DC voltage here. Let us say there is some plus 6 volts at this emitter. Okay. plus 6 volts at this emitter. Let us say there is some plus 3 volts at this collector. I am crudely doing the annotation because I am working through mouse itself. So imagine there is this plus 6 volts at the emitter, plus 3 volts at the collector by means of the biasing. That means across the transistor there is plus 3 volts, which means this transistor is not completely switched on. It is in the active region now. Now let us say we apply a small AC signal here. This AC signal is in millivolts now. Imagine that this AC signal is, let us say, some 2 millivolts. 2 millivolts peak to peak. Imagine that way. Now there is this DC plus 6 volts DC. There is this plus 3 volts AC. But we are DC. We are applying a small AC input. When you apply a small input, this small AC is going to change only in this DC itself. It is going to make a small change of 1 millivolt up and 1 millivolt down. And that is going to cause a change in the collector current as well in millivolts itself. That is how, even though the DC current's flow is in this direction, the DC current flow is in this direction, AC is bidirectional always, right? DC is a direct current which is only one direction, but the AC signal is always bidirectional, which means AC can move from emitter to collector also, AC can move from collector to emitter also. Now when you have 220 volts AC supply at your home, between fuse to neutral, 50 times the direction of current is changing, right? 220 volts 50 hertz means in a second 50 times current is going from phase to neutral, neutral to phase, phase to neutral, neutral to phase. That way AC can travel in both directions. And always in amplifiers, our input signals are AC signals only, because all our natural signals are AC. Even my voice is AC right now. My voice is AC. Why? My vocal cords are moving up and down. When my vocal cords are moving up and down, it is naturally going to produce a signal that is AC. When the bird is moving its wings up and down. Again, if we represent it, that is an AC. Even when a honeybee is flying, its wings are moving and it is up and down, means the signal which is emitted from the honeybee's beating of the wings, that is AC. That way all natural signals are AC. AC does not mean that it is always an electric current. Please understand this. AC does not mean that it is always an electric current. Any natural signal is AC. Sound is AC. Audio is AC. Music is AC. Video is AC. Almost every natural signal is AC. The reason is any signal is produced by means of a vibration of a particular medium. I had given an example of this earlier. If you play guitar or veena or sitar, what is actually happening there? A string is moving to and fro. When the string is moving to and fro, it is emitting a sound. That sound is a wave. That wave is always AC and that wave is in millivolts. Now visualize that sound here. The wave is in millivolts. The sound signal or music is in millivolts. But the transistor is kept in volts. Transistor, we are purposefully keeping it in volts. So a small change of millivolts is going to cause a large change because of this DC itself. We are ingeniously combining AC and DC together so that we achieve the purpose of amplification. That is the basic idea here. That is the basic purpose of setting the quiescent point for the transistor. Okay. So that way, input, even if you think that how emitter can have input, emitter is having an input of AC itself. Now, even if we replace emitter with collector, collector with emitter, the circuit will work in the same fashion. Why? AC signal can move in both directions. As far as AC signal is concerned, there is no collector, there is no emitter. Only for the DC biasing, there is collector, there is emitter. So always amplifiers and oscillators are basically DC circuits which are handling AC signals. Remember this. All the electronic circuitry are basically DC circuits, which means that in those DC circuits only there is a DC power. For example, your mobile phone is basically a DC device, right? It is powered by a 3.6 volts DC battery, which means the mobile phone is basically a DC device. Even the laptop is basically a DC device, but laptop is working through Wi-Fi now, and your mobile phone is working through 3G network. What is that 3G network? 2.4 gigahertz radio frequency. That 2.4 gigahertz is what? AC. Or you speak into your mobile phone, your speech going into the microphone, and from the microphone signal is going all the way. That is also AC. So the whole mobile phone is working with AC signal, but mobile phone circuitry as such is basically DC powered. That is the idea here. All the electronic systems are powered by DC power supply, but they are going to handle AC signals. I hope that is clear now. Is it clear? Is your doubt cleared? Okay, no answer. Let me proceed. So we apply KVL to the entire loop. Okay, you have put your answer in the chat box. Fine. Applying KVL to the entire loop, I showed you that through the annotation, VCC minus ICRC minus VCE minus IERE plus VEE equals 0. Remember the notation which we used? Now based on this, we can have an expression for VCE itself. We had an expression for IE, we had an expression for VCB, now we can have an expression for VCE. So VCE is VEE plus VCC minus IE into RC plus RE, equating IC and IE because they are approximately same. We can have an expression for VCE in this manner. Now using this particular DC analysis, let us solve one exercise. The exercise is find Q point for the given common base configuration. Given beta equals 60, VEE is 4 volts, VCC is 10 volts, and RC is 2.4 kilo ohms, RE is 1.2 kilo ohms. We can straight away apply all the equations. IE is 4 minus 0.7 divided by 1.2. You apply KVL to the input loop. VEE minus VBE divided by RE. So 4 minus 0.7 divided by 1.2. That K I have not put there. You will have to visualize K. Later on in the PPT I will correct it. Let me put K later on. So 4 minus 0.7 divided by 1.2 kilo ohms is nothing but 2.75 milliamps. That is IE. Now when we find IE, we can find IB because beta is given. IB is nothing but IE divided by 1 plus beta. That is 2.75 milliamps divided by 61 is 45.08 microamps. When we find out IB, we can find out IC. IC is IB into beta, 45.08 microamps into 60, 2.71 milliamps. You can see a small difference between IE and IC. In most of the cases, we can approximate them. Here the difference is only 0.04 milliamps or 40 microamps. That is in terms of the IB itself. So IC is 2.71 milliamps. We got one coordinate of the Q point. Now we can find out VCB. Applying KVL at the output side, we can find out VCB is 10 minus ICRC. Okay, 10 minus IC is 2.71 milli, RC is 2.4 kilo, that milli and kilo get cancelled, and we can have VCB equal 3.5 volts. Once we have VCB, we can find out VCE. VCE, applying the same loop for the complete, applying the KVL for the complete loop. We can write 4 plus 10 minus 2.75 into 3.6 equals 4.1 volts. 4 plus 10, VEE plus VCC minus IE into RC plus RE. IE is 2.75 milliampere, RC plus RE 2.4K plus 1.2K is 3.6K. Here, instead of IC, I have put IE. You can put IC also, because In the output loop it is IC, in the input loop it is IE, but we are approximately equating them. So that way we get VCE equals 4.1 volts. So across collector to emitter there is this 4.1 volts, which indicates that the transistor is not in the operating in the saturation region, it is operating in the active region. Okay, that is how this analysis is proved. Now we are coming to the last part of the DC analysis. Later on we will start the AC analysis of the same circuits. We have discussed common emitter configuration. There we had discussed 3 biasing methods. Then we discussed common collector configuration yesterday, and today we have discussed common base configuration. Let us discuss a little more about what is meant by stability. Factors that affect the stability of the Q point. Now in any circuitry, whether it is common base, common emitter or common collector, in any such circuitry, what we want is, we want the Q point to be highly stable. For example, in this circuit itself, if we have designed the circuit for VCE equals 4.1 volts and IC equal 2.71 milliamps, we expect that the circuit will always work only with these two coordinates of the Q point, and we expect that the transistor will always remain in the active region. But it does not happen because of certain factors. Those factors I had discussed earlier. I am summarizing this now again. You can look at these things. Now we have the factor called beta, we have the factor called VBE, and we have the factor called ICO. ICO is in general called as reverse saturation current. Recall the basics which you have studied about diode in either engineering physics or in basic electronics, where for the diode you have studied an equation of the current. So in the expression for the diode current, always the reverse saturation current used to come into picture. Reverse saturation current means the current that is flowing through the junction when the junction is reverse biased. Always in any semiconductor, there are majority carriers and there are minority carriers. Always there will be minority carriers, and even the minority carriers are going to contribute the electric current. So as transistor is nothing but 2 PN junctions, base to collector and base to emitter, there are 2 PN junctions. Even in case of a transistor, the reverse saturation current comes into picture, because even in a N-type transistor, N-type region, there can be holes. Even in a P-type region, there can be electrons, because in nature there is nothing called completely pure item anywhere. In nature it is always a mixture of many things. Even when people sell gold in a jewelry shop, they will never say 100% pure gold. They will always say 24 karat gold. 100% pure gold may not be possible at all, because always there will be some trace elements within any particular material, which means that in nature, as nature is composed of more than 100 elements, you already know the periodic table which you have studied in chemistry. There are more than 100 elements. All these elements mix up in many different ways. There are solids, there are liquids, there are gases. All this mix up in many different ways, and that is what is nature basically. So in nature we cannot have completely pure material in any case. So even when we have a purity of N-type semiconductor or P-type semiconductor, we will have always some impurities within these materials, and we will always have some type of imbalances which is going to lead to minority carriers as well. So because of the minority carriers, we have the current which is contributed to the movement of those minority charge carriers. Now you can see here at minus 65 degrees centigrade, the reverse saturation current is 0.2 milliamp, 0.2 milli into nano. The unit here is nanoampere, 0.2 into 10 power minus 3 nanoampere, which means it is actually 0.2 into 10 power minus 12 ampere or 0.2 picoampere at minus 65 degrees centigrade. At 25 degrees centigrade, the reverse saturation current is 0.1 nanoampere. At 100 degrees centigrade, the reverse saturation current is 20 nanoampere. At 175 degrees centigrade, the reverse saturation current is 3.3 into 10 power 3 nanoampere, which means 3.3 into 10 power 3 into 10 power minus 9. It is 3.3 into 10 power minus 6. That means 3.3 microamperes. Now you can see when the temperature increases, the reverse saturation current increases. Why? When the temperature increases, the charge carriers will gain energy from the temperature. Always the electric current is directly proportional to the temperature. More the temperature, more is the flow of charge carriers, because temperature itself is the source of energy for the charge carriers. Even in your body also, you can observe whenever you have a fever, when the temperature of the body increases, heart will be pumping more blood and there will be rapid respiration in the body as well. Breathing rate increases, blood flow increases, so as to energize the body, so as to combat with the germs. That is where fever occurs there. So when temperature increases, there is increase in the reverse saturation current. Now when the temperature increases, there is increase in the beta as well. Why there is increase in the beta as well? When the reverse saturation current increases, that contributes to the forward current as well. You will have to recall the diode current equation, where the main current increases even when the reverse current increases. That is a strange phenomenon that is happening inside the semiconductors. There is something called diffusion current, there is something called drift current, that we will discuss later on about what is meant by diffusion current and what is meant by drift current. Okay, there is a doubt. If temperature increases, resistance also increases. How does current value increase? If temperature increases, resistance does not necessarily increase. Resistance can reduce also. It depends on the particular material. I am going to discuss those things later on. There is something called thermistor, there is something called sensistor. Any material can have a positive temperature coefficient also, and any material can have a negative temperature coefficient also. So it does not mean that when the temperature increases, resistance also increases for all the materials. It is not so. It is selective there, because we have conductors, we have semiconductors, we have insulators. We have different types of materials. All these materials will have different types of properties. So don't come to a conclusion that when temperature increases, resistance increases. It does not do that. But when temperature increases, current definitely increases. Why? What is current? Current is the flow of charge carriers. Basically, it is the flow of electrons. When there is increase in temperature, naturally electrons will be moving with the higher speed, because electrons are attaining that energy by the temperature itself. So when the reverse current increases, even the forward current also increases. When the forward current increases, naturally beta also increases. You can see that at minus 65 degrees centigrade, if beta is 20, at 25 degrees centigrade beta is 50, at 100 degrees centigrade beta is 80, at 175 degrees centigrade beta is 120. It is for the same transistor. You can see the circuit. For the very circuit which we are using, now the beta given 60, it is given only in the ambient temperature, the normal temperature. We generally take it as either 25 degrees centigrade or 27 degrees centigrade. Normally all over the globe, we take it as 25 degrees centigrade. At times we also take 27 degrees centigrade. So that is the normal temperature. But at different temperatures, same transistor will have different beta. So recall the point which I was telling earlier, that even if we have a best bias in circuitry also, it is it is affected to some extent, its Q point gets affected to some extent. So we have to have a circuit which should not depend on beta itself. That was the point I was telling you from the beginning, that we want to have a biasing circuitry where the Q point should remain stable, means we should not consider beta at all. That is when we discussed the voltage divider bias at length, and that is when we also discussed the accurate analysis and the approximate analysis. And we have a condition for the approximate analysis, that beta into Re must be greater than or equal to 10 R2. Then we know beta, but if we meet the condition between that R2 and Re, then we can completely ignore beta for that particular biasing circuitry. This was not possible with self bias and fixed bias. It was possible with voltage divider bias. That is when I was telling you that the voltage divider bias is the highly popular circuit which we are going to use in all our circuitry. So now you can admire the voltage divider bias circuitry itself, that we can work with that particular circuitry independent of beta, because beta changes with temperature. Not only beta, even VBE changes with temperature. You can see this here. At minus 65 degrees centigrade, VBE is 0.85 volts for the varied transistor which you are seeing on the screen now. VB is 0.85 volts. At 25 degrees centigrade, VBE is 0.65 volts. In general, we take it as 0.7 volts for a silicon transistor. Always we used to substitute 0.7. Here also for IE, 4 minus 0.7, we have substituted, assuming that we are working with 25 degrees centigrade. So it is around 0.65 volts. We make it as a round figure there, that's all. At 100 degrees centigrade, VBE is 0.48 volts. At 175 degrees centigrade, VBE is 0.3 volts. That means the very diode, VBE, is nothing but a diode between base and emitter. The very diode where you assumed till now that across the diode it is always 0.7 volts, that is wrong. It is 0.7 volts at a given temperature. When the temperature changes, VBE also changes. That is when I gave you the examples of a satellite. A satellite is subjected to all types of temperatures. Below 0 degree also, above 0 degree also. And let us say we have a submarine. In a submarine, there are electronic circuitry. Submarine is moving below the surface of water now. Let us say submarine is moving in the ocean now. Now, in the submarine, there are people there inside the submarine and they are working with the equipments. Electronic equipments are there. There are, again, communications among the submarines. There is a special technology called sonar, sound navigation and ranging, by means of which they can communicate with each other. Now, think that in the submarine, the temperature can go lesser, but still the electronic circuitry should work there. Now, let us say there is a space station 300 kilometers above Earth. There is a space station now. And in the space station, maybe if it is subjected to sunlight always, temperature can be increasing. But our electronic circuitry should work at all temperatures, which means we cannot be dependent on beta, we cannot be dependent on VBE also. That means, now you observe this table, here reverse saturation current is increasing with increase in temperature, beta is increasing with increase in temperature, but VBE is reducing with increase in temperature. Can anybody tell me why? Either you unmute and tell me, or you put the answer in the chat box. Can you tell me why? When temperature increases, reverse saturation current increases, beta increases, but VBE reduces. Can anybody tell me why? Okay, no answer from the students, so I'll only tell. See, when the current increases, naturally voltage will reduce. Why? This VBE, base to emitter junction, is a semiconductor material. It is a non-linear device. Transistor is a non-linear device, whereas resistor is a linear device. Ohm's law is applicable to a resistor. Ohm's law is not applicable to a transistor or a diode. You got the point? Always a diode characteristics is a non-linear curve. It is not a straight line. You cannot apply that y equals mx plus c equation for the diode's input characteristics or output characteristics. Even for the transistor's input as well as output characteristics, we cannot apply Ohm's law. Why? Because it is a combination of two different materials. One is p-type, one is n-type. Transistor is a combination of three different materials: n-type, p-type, n-type. Emitter is heavily doped, collector is medium doped. Collector is large, emitter is medium, base is small. That way it is a dissimilar combination of dissimilar materials. So a transistor is a non-linear device. In case of a transistor, there is no expression for its resistance as such directly. Here when the current increases, voltage across that junction reduces because it is conducting more now. When it is conducting more, its resistance is reducing. When the resistance is reducing, it is becoming 0.3 volts. Here when it was minus 65 degrees centigrade, resistance was slightly more, so the voltage across the base to emitter junction was 0.85 volts. At 175 degrees centigrade, because of the increasing the current, the resistance got reduced there and the voltage across the base to emitter junction is only 0.3 volts. That is why we say the transistor or the diode will have a dynamic resistance. Means the resistance of active devices is never a constant thing. It can vary based on the way in which it is biased or based on the way in which the ambient temperature is there. Okay. So now, why all these things are discussed in detail? In electronics, even the smallest thing will become more important for us. Because in electronics, we work with those charge carriers which we cannot see at all. We work with those signals which we cannot see at all. Sound signal we cannot see, radio signal we cannot see, but we will have to amplify them. And electrons we cannot see, but we will have to work with the devices where current is because of the flow of electrons itself. So even a small change can result in a much larger change because we are going to use amplifiers. Just to give you one more live example, I am speaking into the microphone now. In the microphone, it is now a few millivolts. That millivolts goes into the laptop now. In the laptop, it is going to digitize. My voice is going to be converted into a digital form. There is an analog to digital converter in the laptop. That digital signal is going into a DSP now inside the laptop. There is something called digital signal processing. So it is going into a DSP now. From the DSP, it is going into a modulator now. From the modulator, it is going to the Wi-Fi antenna now. So from the modulator, when it is going to the Wi-Fi antenna, there my voice is digitized. It is no more in millivolts. It is in few volts now, because this voice has to reach the destination. The destination is either your mobile phone or your laptop now. In between, we have free space, which is used as a communication medium. Now think about it. In the free space, millivolts cannot move. Only volts can move. Sometimes it can be more than volts also. If a satellite is sending its signal all the way to Earth, it will not be in volts also. It will be more than volts. So in that manner, in electronics, we deal with all types of amplifiers. Audio amplifiers, radio amplifiers, video amplifiers. So when we use those amplifiers, even a small change is going to affect the performance. That is when I stress again on the stability of the voltage divider bias circuitry. Okay. Now these are the factors which are affecting the stability of the Q point, and we already know how we have combated with these particular variations by going for that approximate analysis of voltage divider bias with the given condition there. Now with this I will end today's class. In the next class I will come back to the stability of the Q point in the PDF there, where we have some circuitry where we have better ideas to stabilize the biasing. So I will conclude today's class. See you in the next class.